A dead star the size of a city can weigh more than the sun, bend its own light, crack its crust under magnetic stress, and spin like a cosmic lighthouse in the dark. Neutron stars are not just the remains of ancient supernovae. They are some of the strangest survivors in the universe, holding matter so compressed that ordinary atoms lose their familiar shape. In this slow journey from collapse to pulsars, magnetars, starquakes, and collisions that may forge gold. Boring Science Stories follows the quiet power of these impossible remnants. Thank you for spending your time here and letting this science story become part of your day or night. If this kind of calm cosmic mystery helps you relax, please like the video, subscribe to the channel, and share it with someone who enjoys drifting through the universe slowly. What time is it where you're watching, and where in the world are you listening from? Leave a comment below. Now, let us gently enter the strange world of neutron stars. The path toward a neutron star begins before any explosion, inside a massive star that has spent its life holding gravity at bay. For millions of years, the star exists because two opposing pressures remain in uneasy balance. Gravity pulls every layer inward, trying to gather the star into a smaller and smaller volume, while fusion in the core releases energy that pushes outward through the surrounding gas. The star is not quiet, even when it appears steady from a distance. It is a furnace organized by its own weight, a structure held open by heat, radiation, and the continual rearrangement of atomic nuclei. Hydrogen gives way to helium, helium gives way to heavier elements, and the inner regions become layered with the products of earlier burning. A star massive enough to end as a neutron star does not merely shine until its fuel is gone. It builds a sequence of deeper and hotter cores, each one less patient than the last, until the material at the center reaches a point where the old balance can no longer be repaired. That point arrives when the core becomes rich in iron. Iron is not just another step in the chain. It is a boundary in stellar life, because fusing iron does not release useful energy in the way earlier reactions do. The core has reached a kind of energetic dead end. For as long as lighter elements were being fused, the star could keep producing outward pressure. Once iron dominates the center, that support begins to fail. Gravity has not changed its intention. It has been waiting through the entire life of the star, present in every layer, pressing inward with the combined weight of the material above. When the core can no longer answer with enough pressure of its own, the star begins to lose the argument that once made it luminous. Collapse starts not as a slow fading, but as a physical failure. The inner core contracts, the surrounding layers follow, and matter that once occupied a huge stellar volume is forced into a region far smaller than any ordinary object made of atoms can tolerate. This is the first strange turn in the story of neutron stars. They are born not because a star simply dies, but because the matter inside a dying star runs out of ways to remain ordinary. The atoms in the collapsing core are pushed together with such violence that the spacing between them becomes irrelevant. In everyday matter, most of the volume is empty space around tiny nuclei and their electrons. In a collapsing stellar core, that emptiness becomes a weakness. Gravity removes it. Electrons are driven into protons, and the old distinction between the architecture of atoms and the particles inside their nuclei begins to break down. What remains is dominated by neutrons, particles with no net electric charge, packed so closely that the remnant resembles an enormous atomic nucleus more than a familiar star. The transformation is not gentle. It happens because the alternative is continued collapse, and the only resistance left comes from forces acting at nuclear scales. The result is an object that seems almost contradictory. It is a star, but it is no longer burning like a star. It has mass comparable to the sun, but its width is closer to that of a city. It is made from the remains of something once vast enough to govern a whole planetary system. Yet the remnant itself could fit between suburbs on Earth. The reduction is so extreme that the language of size begins to separate from the language of importance. A neutron star is small in diameter, but it is not small in consequence. Its gravity, density, magnetic field, and rotation preserve the violence of its birth in a compact form. Much of what made the original star powerful has not vanished. It has been compressed. This compression is what prevents every massive stellar death from becoming the same ending. The most massive cores continue inward beyond the ability of known pressure to halt them, crossing into black hole formation, where the collapse produces an event horizon. Less massive remnants do not escape collapse, but they do stop before that final boundary. The difference is not one of calm versus catastrophe. Both endings are catastrophic. The difference lies in whether the crushed core finds a last source of resistance before space-time itself closes around it. In the neutron star, that resistance is enough to create a surface. There is still an outside, still a crust, still light that can escape, though distorted by gravity. The object remains visible to the universe, even if its conditions are nearly impossible to reproduce or imagine directly. This middle ground between ordinary stars and black holes gives neutron stars their unusual power. They belong to the visible universe, but only barely. They are compact enough to bend light strongly, dense enough to force matter into unfamiliar states, and energetic enough to announce themselves across great distances. Yet they remain objects with measurable size and structure. Their surfaces can cool, their magnetic fields can evolve, their spins can slow, they can orbit companions, pull matter from nearby stars, collide with one another, or, under the wrong conditions, lose the last resistance that keeps them from becoming black holes. Their existence shows that stellar death is not a single destination, but a set of thresholds. A star crosses one threshold when fusion can no longer support its core. It crosses another when atomic structure is crushed into neutron-rich matter. It may cross a further threshold if the remnant grows too massive for even that matter to hold. Each boundary reveals a different way the universe handles weight. The first is answered by explosion. The second is answered by compression. The third may be answered by disappearance behind an event horizon. Before those later possibilities arise, the birth of the neutron star leaves an outward sign. The collapse of the core and the rebound of the surrounding material produce a supernova, one of the most luminous events associated with stellar death. The outer layers of the star are torn away and thrown into space, carrying newly made elements into the surrounding interstellar medium. The blast can outshine whole galaxies for a short time, but the remnant at the centre is quieter and stranger than the light around it suggests. In the aftermath, where a star once filled an enormous region, there remains a compact object only a few tens of kilometres across. It is hot, dense, and newly formed, spinning rapidly because the angular momentum of the original star has been concentrated into a much smaller body. The same principle that makes a skater spin faster when drawing in the arms becomes almost severe at stellar scale. Shrink the star enough, and rotation that once seemed ordinary becomes astonishing. This is why the first stage of a neutron star's life can already contain the seeds of later strangeness. The core does not merely become dense, it becomes dense while turning, magnetized, and surrounded by the expanding remains of the explosion that made it. The supernova remnant spreads outward, while the neutron star remains near the center, like a hard point left behind by a broken engine. Over time, its radiation may sweep through space in beams, its magnetic field may guide charged particles. Its surface may settle into a crust far stronger than ordinary matter. But all of those later traits begin with the same essential fact. Gravity has compressed a stellar core into a form where matter is close to the edge of what can remain matter at all. This is why neutron stars are not merely smaller versions of stars. A normal star is defined by energy flowing outward from fusion. A neutron star is defined by the aftermath of fusion's failure. Its power comes not from the steady burning of fuel, but from compactness, rotation, magnetism, and the lingering heat of collapse. It is a remnant, but not a passive one. The dead core continues to shape its surroundings because density itself has become active. Nearby matter feels the pull. Light passing close to the surface follows curved paths. Any remaining atmosphere is pressed into an almost impossibly thin layer. The star has lost the wide, luminous body it once had, but it has gained a different kind of influence, one that comes from placing enormous mass inside a very small boundary. There is a quiet lesson in that transformation. The universe does not treat death as simple disappearance. In massive stars, death can mean the concentration of everything that once held the star together into a surviving remnant of almost unbearable intensity. The neutron star is the point where a stellar life narrows instead of ending cleanly, where the spacious architecture of a star becomes a dense sphere of nuclear matter, and where the old outward fire gives way to inward force. It stands as an answer to collapse that is not yet a black hole, a final hesitation before complete gravitational surrender. The story has only reached the outer edge of that object, but already the scale has changed. The next question is no longer only how such a remnant forms, but what matter must become in order to survive there. The neutron threshold is reached when the familiar architecture of matter can no longer defend itself against the inward force of collapse. In ordinary conditions, atoms are spacious things. Their nuclei contain protons and neutrons, while electrons occupy regions around them, and almost everything that seems solid is held in shape by electromagnetic forces that keep particles from simply passing through one another. Stone, water, metal, bone, air, and the layered plasma inside a living star all depend on that hidden arrangement. Matter feels continuous because atoms resist compression at everyday scales, but the resistance is not unlimited. Inside the collapsing core of a massive star, the pressure rises far beyond the range where chemical structure has any meaning. There are no molecules left to preserve, no crystals or fluids in the ordinary sense, and no stable atomic shells. The core becomes a place where the old categories of matter are stripped away one by one, until the question is not what substance the star contains, but what kind of particle arrangement can still exist under such weight. The first great casualty is the electron's independence. Electrons normally help define the size of atoms, giving matter its volume and much of its everyday behavior. Even in a white dwarf, the compact remnant left by a lower mass star, electrons still play a crucial role. They are packed tightly enough to create a quantum pressure that resists further collapse. This pressure does not come from heat, but from a rule of nature that prevents identical particles from occupying exactly the same state. In a white dwarf, that rule is strong enough to hold up the dead star against gravity, at least if the mass remains below a certain limit. But the core that will become a neutron star is heavier and more violently compressed. Electron pressure is no longer enough. Gravity continues to force the material inward, and the electrons are pressed into the protons in atomic nuclei. In that collision of identities, a proton and an electron can combine to form a neutron, releasing a tiny particle called a neutrino. Neutrinos are difficult to stop. They interact so weakly with matter that most pass through planets, stars, and human bodies as though almost nothing is there. During core collapse, enormous numbers of them are produced, and for a brief time they carry away a vast part of the energy involved in the death of the star. Their escape is one sign that the core is not merely being squeezed, it is being transformed. Protons are losing their separate positive charge. Electrons are being removed from the role they once played in shaping atoms. The balance that allowed matter to have familiar volume is replaced by a denser arrangement dominated by neutrons. This is why the name neutron star is not just a label of convenience. It describes the central change that allows the remnant to stop before becoming a black hole. The star is not made entirely of free neutrons in every layer, and its structure is more complicated than the name suggests. But the collapse has driven matter toward a neutron-rich state. The core becomes less like a collection of atoms and more like nuclear material extended to stellar scale. A nucleus inside an atom is already extremely dense. Because protons and neutrons are packed together by the strong nuclear force, a neutron star takes that kind of density and gives it astronomical mass. It is as though a principle usually confined to the centre of atoms has been enlarged until it becomes a star. The comparison is imperfect, but it points toward the reason these objects feel so foreign. They are not held up by ordinary pressure in the way a living star is. They are held up by quantum rules and nuclear interactions operating under conditions close to their limits. The collapse does not proceed smoothly all the way inward because neutrons, like electrons, are subject to exclusion. They cannot all be forced into the same quantum state. When the density becomes high enough, neutron degeneracy pressure begins to resist gravity. This pressure is strange because it does not require warmth in the ordinary sense. A neutron star can cool over time and still remain supported by the quantum behavior of the particles inside it. Heat may influence its surface and early evolution, but the deeper support comes from matter being packed so tightly that the particles themselves oppose further compression through the laws that govern the microscopic world. In this way, the neutron threshold is not only a point in a star's collapse, it is a point where the small-scale rules of physics become the main architecture of an astronomical body. Yet this resistance is not absolute. It is a last support, not an infinite one. If the remnant is too massive, or if later events add enough material, the forces that support neutron-rich matter may fail. Then the object can continue inward toward black hole formation. A neutron star therefore exists inside a narrow range of possibility. It is heavy enough to crush atoms, but not so heavy that all surfaces vanish. It is compact enough for gravity to dominate every visible property, but not compact enough to hide itself completely. The matter inside it has survived one kind of collapse by entering a new state, but it remains close to the edge of another. That nearness gives neutron stars much of their scientific importance. They are natural laboratories for matter at densities that human experiments cannot fully recreate. On Earth, physicists can study atomic nuclei, particle interactions, and the behavior of matter under high pressure, but no laboratory can assemble a sun's worth of material into a city-sized sphere and hold it there. The neutron star performs that experiment by existing. Its mass, radius, temperature, magnetic field, spin, and gravitational effects all become indirect clues to the behavior of matter at the threshold between nuclear density and deeper collapse. The difficulty is that these clues are not easy to read. A neutron star is distant, small, and surrounded by effects that complicate interpretation. Light leaving its surface is shifted by gravity. Radiation may be shaped by magnetic fields. The star may rotate rapidly, distorting the signal. Matter falling onto it from a companion can mask what the surface itself would otherwise reveal. Even the exact relationship between mass and radius remains one of the most important unresolved measurements, because it carries information about how dense matter responds to pressure. This relationship is called the equation of state, a plain name for a deep question. When matter is squeezed beyond the range of atoms, how stiff or soft does it become? if the matter is stiff. A neutron star of a given mass can maintain a larger radius. If it is softer, the same mass may compress into a smaller sphere. The difference is not just a detail. It can decide how close the star is to collapse, how it vibrates after a disturbance, how it behaves during a merger, and what signals it sends into space. Under the crust, the particles may not remain in any simple arrangement. Some models suggest that at extreme density, neutrons and protons may give way to more exotic forms involving particles rarely seen outside high-energy physics, or even matter described in terms of quarks, the smaller constituents inside protons and neutrons. These possibilities remain cautious and uncertain. A calm approach requires keeping the known transformation separate from the speculative one. It is known that neutron stars are compact remnants produced when massive stellar cores collapse and become dominated by neutron-rich matter. It is not yet known exactly what happens at the deepest center of the most massive neutron stars. The boundary between evidence and interpretation matters here, because the object itself sits at a boundary. Its outer existence is visible through pulses, heat, gravitational effects, and X-ray emission. Its inner state must be inferred from how those signals behave. The neutron threshold therefore has two meanings. It is the physical crossing that happens during collapse, when electrons and protons are forced together and ordinary atomic structure disappears. It is also the scientific threshold beyond which direct intuition becomes unreliable. Matter no longer behaves like the substances familiar from planets or living stars. Density stops being a simple measure and becomes a doorway into unknown forms. A neutron star is not only dense because its material is packed tightly, it is dense because almost every simple description has been compressed as well. The words solid, liquid, gas, metal, atmosphere, surface, and core still appear, but each one has to be used with care, because none of them means quite what it would mean on Earth. The remnant left by collapse is therefore a lesson in how nature changes the meaning of matter when pressure becomes extreme enough. The star begins with familiar particles and ends with a body that can only be understood by joining gravity, nuclear physics, quantum rules, and astronomical observation. In that joining, the neutron becomes more than a neutral particle inside an atom. It becomes the central sign of a larger transformation, the clue that the dead star has crossed from the world of atoms into the world of nuclear matter. This supernova provides the light, but the neutron threshold provides the remnant. Once that threshold is crossed, the story of the star is no longer about fuel running out. It is about what remains when matter is forced to find one final way to resist being crushed completely. The birth of a neutron star is hidden inside the violence of a core collapse supernova, but the event begins with a failure that is almost simple. At the center of a massive star, iron has gathered where lighter fuels once kept the interior alive. The surrounding layers still carry enormous weight. The star still looks like a star from the outside, wide and luminous, but the core has reached a stage where adding pressure through fusion is no longer possible. Iron cannot keep the same outward support going, and the innermost region begins to contract under its own gravity. At first, the collapse is local, a deep inward motion in the part of the star where the pressure has weakened most severely. Then the motion becomes contagious. Layers above the core fall after it, not because they are pulled by a single surface, but because the support beneath them has been removed. The star is suddenly like an enormous structure whose central columns have vanished. Material that once hovered in balance begins to rush inward, and the scale of the fall is difficult to keep in ordinary language. Matter descends through the core at a large fraction of the speed of light, while density rises so quickly that the old atomic order cannot survive. Electrons are pressed into protons, neutrinos are produced in extraordinary numbers. The core becomes smaller, hotter, and more tightly bound with each moment, until the collapse meets a resistance that does not belong to chemistry or ordinary heat. It is the resistance of nuclear matter being forced into a region where particles can no longer be packed without consequence. That resistance does not calmly stop the star. It produces a rebound, a sudden change in motion at the heart of the collapse. The inner core stiffens when it reaches nuclear density, and the material falling from above crashes into this newly resistant center. For a brief interval, the direction of the story changes. Infilling matter is decelerated, compressed, and driven outward as a shock wave begins to form. This shock is not yet the full explosion. It must fight its way through the surrounding layers, losing energy as it breaks apart heavy nuclei and as neutrinos escape from the collapsing interior. The early shock can stall, and for a time the star seems to hang between two endings. If the shock cannot be revived, the collapse may continue into a black hole. If energy from the flood of neutrinos and the churning motion of the core helps drive the shock outward, the star tears itself open. This in-between moment is one of the most important uncertainties in the physics of supernovae. The broad outline is known, but the detailed mechanism is difficult because it involves gravity, nuclear matter, radiation, turbulence, magnetic fields, rotation, and neutrinos moving through matter at densities beyond any laboratory setting. A supernova is often remembered for its light, but the first decisive drama takes place in darkness, buried under layers of stellar material that are still falling. The visible explosion is the delayed announcement of what has already happened in the core. When the shock finally breaks through the star, the outer layers are launched outward into space. Gas that once belonged to a single star becomes an expanding shell of heated matter. Elements made during the life of the star, and others assembled in the violence of the blast, are scattered into the surrounding galaxy. The event can shine with enough brilliance to be seen across immense distances, but its light is only one part of the story. The supernova is both a destruction and an uncovering. It removes the outer body of the star and reveals the compact remnant left in the center. Where there had been a furnace spread over millions of kilometers, there is now a newly born neutron star only about the width of a city. The contrast is not a metaphor. It is the direct result of gravitational collapse concentrating the core into a dense remnant while the rest of the star is expelled. In the first moments after birth, the neutron star is intensely hot. Its surface and interior carry the memory of the collapse, and neutrinos continue to pour away from it, cooling the object while barely interacting with the surrounding matter. The newborn remnant may also be spinning rapidly. Whatever rotation the original core possessed has been compressed into a far smaller radius, and that shrinkage greatly increases the spin. The effect is familiar in principle, but extreme in scale. A body that contracts while preserving angular momentum must rotate faster, and in a neutron star that acceleration can turn a dead core into one of the fastest rotating natural objects known. At the same time, magnetic fields that were once spread across a much larger volume can be intensified by collapse. The field lines are squeezed closer together. And if rotation and internal motion amplify them further, the remnant may emerge as an unusually magnetized object. Not every neutron star is born the same way in detail. Some receive kicks from asymmetries in the explosion and race away from the site of their formation. Others remain near the center of glowing supernova remnants, surrounded by expanding shells and filaments that still mark the death of the parent star. The kick is a reminder that a supernova is rarely perfectly even. If one side of the explosion is stronger than another, or if neutrino emission and matter flows are not symmetrical, the remnant can be thrown into space at high speed. A star that spent its life fixed within a larger stellar system may leave as a compact runaway, carrying its mass, spin, and magnetic field into a different region of the galaxy. The supernova therefore does more than make a neutron star. It gives the remnant its first motion, its early environment, and part of its long future. Around the new object, the expelled material continues to expand. In some cases, this glowing debris becomes a recognizable nebula, a record of the explosion written in gas and dust. The Crab Nebula is one of the clearest examples, with a pulsar at its center whose rotation continues to energize the surrounding material. In such remnants, the link between supernova and neutron star becomes almost visible. The expanding cloud is the discarded body of the star. The pulsar is the surviving core. Energy flows from the rotating neutron star into the surrounding nebula, keeping it bright long after the original explosion. This connection explains why neutron stars can remain important even after the brief brilliance of the supernova fades. The explosion lasts for a short astronomical interval, but the remnant can influence its surroundings for thousands, millions, or even billions of years. The birth event also decides whether the remnant remains a neutron star at all. The mass left behind after collapse is critical. If the core is too light, the original star may not produce a neutron star through this pathway. If it is too heavy, the newborn object may briefly form and then collapse further into a black hole, or may never stabilize as a neutron star in the first place. The final result depends on the mass of the core, the amount of material expelled, the details of fallback, and the nature of dense matter itself. Fallback occurs when some material launched outward fails to escape and returns toward the center. If enough of it lands on the remnant, it can push the object closer to instability. A neutron star is therefore not simply made at the instant the core rebounds. Its survival may still depend on what the explosion succeeds in removing. This gives the supernova a double role. It creates the remnant by compressing the core, and it protects the remnant by carrying away enough mass to prevent further collapse. The quiet irony is that the neutron star survives because the larger star is destroyed thoroughly enough. The blast clears away material that might otherwise fall back and push the core beyond its limit. The violence of the explosion is not separate from the existence of the remnant. It is part of the condition that allows a surface to remain. After the shock, after the neutrino flood, after the expanding shell begins its journey into interstellar space, the newborn neutron star settles into a different kind of life. It no longer burns in the ordinary stellar sense, but it is not inactive. It cools, it spins, it radiates. It may pulse if its beams sweep across the right line of sight. It may pull matter from a companion if one remains nearby. It may become part of a binary future that ends in another collision far later. All of those later histories begin in the same compressed moment, when iron fails, the core collapses, and the star answers its own weight with one final outward blast. The supernova is the bright signature, but the neutron star is the concentrated consequence. What remains in the center is not the star as it was, and not yet the silence of a black hole. It is the exposed heart of collapse, held at the edge by nuclear pressure, carrying the marks of the explosion that made it, and waiting for its strange properties to reveal what kind of object has been born. A neutron star is often described by its size first, because the measurement creates an immediate break with ordinary expectation. A remnant that may contain more mass than the Sun can be only a few tens of kilometers wide, close enough in scale to a large city that the comparison almost sounds too modest for the object being described. The problem is that the city comparison works only for diameter. It fails almost everywhere else. A city is spacious, full of air, streets, water, stone, steel, empty interiors, and open sky. A neutron star is the opposite of spacious. It is what remains when a stellar core has been stripped of nearly every ordinary way to occupy volume. The mass that once belonged to a vast interior is pressed into a sphere so compact that the distance from one side to the other can be crossed by light in a tiny fraction of a second. Yet the gravity of that same sphere is powerful enough to make space around it deeply curved. The mind can hold the size for a moment, but not the density. That is where the true difficulty begins. Density is a simple word for a severe idea. It means mass per volume. But in a neutron star, the word stops behaving like a household measure and becomes a statement about matter near nuclear packing. On Earth, density can separate cork from iron, air from water, rock from metal. Inside a neutron star, those comparisons fade away. The material is not merely heavy, it is compressed past the architecture that makes ordinary substances possible. A small amount of neutron star matter would outweigh mountains if it could somehow be brought into ordinary conditions. Though such a transfer is not a realistic physical act, the comparison is useful only because it hints at the scale. What makes neutron star matter extraordinary is not that it is a familiar substance made heavier, but that the particles have been forced into a state where the empty space of atoms has almost entirely vanished. The mass is no longer distributed across the large interior of a living star. It has been gathered into a sphere whose surface lies close to the centre by stellar standards. This small radius has consequences that spread through every property of the object. Gravity becomes intense because the same mass is concentrated into a much smaller region. Rotation becomes rapid because the collapsing core preserves angular momentum while shrinking sharply. Magnetic fields can become stronger because field structures are compressed and reorganized. Even the way light leaves the surface changes, because the star is compact enough for gravity to alter the path and energy of radiation. Size, in a neutron star, is not an isolated fact. It is the condition that makes the other strangeness possible. A larger star can be luminous, unstable, enormous, and dramatic. But its matter is spread widely enough that many regions remain relatively loose by comparison. A neutron star takes the same language of stellar mass and removes the space that made that language feel familiar. One of the most counterintuitive features is that adding mass to a neutron star does not necessarily make it larger in the ordinary sense. For planets, and many everyday objects, more material often means a larger body. For neutron stars, the relationship is more difficult. Additional mass increases gravity, and stronger gravity can compress the star further. The exact behaviour depends on the still uncertain properties of dense matter. But the general lesson is clear enough. A heavier neutron star may have a smaller radius than a lighter one. This reversal shows how far the object has moved from ordinary intuition. It is not being built like a pile of stones. It is being held in a contest between gravity and the resistance of matter at nuclear density. More mass strengthens one side of that contest, forcing the other to answer under conditions that become increasingly unforgiving. Near the upper limit, the distinction between a stable neutron star and a black hole may depend on a narrow difference in mass and on the true stiffness of matter in the core. If dense matter can resist compression strongly, the star can remain larger for a given mass. If it yields more easily, the same mass can fit into a smaller radius and may approach collapse more closely. This uncertainty turns each well-measured neutron star into a clue. A precise mass matters. A precise radius matters even more, because together they reveal how the star's interior is responding to pressure. A city-sized sphere with solar mass is therefore not just a spectacle. It is an instrument built by gravity, testing matter in a regime that no laboratory can reproduce. The surface gravity follows from the compactness. Standing is not a meaningful idea there, but the comparison to standing helps reveal the scale. On Earth, Gravity is gentle enough for mountains to rise, oceans to move, atmospheres to spread, and living bodies to remain intact. On a neutron star, gravity is so strong that a raised feature cannot grow high without being crushed. Any normal object approaching the surface would be stretched, heated, broken, and forced into the star's gravitational order long before ordinary contact could matter. The escape speed is a significant fraction of the speed of light, meaning that leaving the surface would require an immense amount of energy. Even photons, which always travel at light speed locally, lose energy as they climb away from the gravitational well. Their wavelengths stretch, and the radiation appears redder to a distant observer. This gravitational redshift is not decorative. It is one of the ways compactness becomes measurable from far away. The star's small size also changes visibility. A neutron star is difficult to see directly because its surface area is tiny compared with that of ordinary stars. Even when extremely hot, it does not present a large glowing disk to the universe. Its light must be detected through X-rays, pulses, thermal emission, or interactions with surrounding material. A living star announces itself through broad radiance. A neutron star often announces itself through precision, through repeated flashes, energetic outbursts, or the effect it has on matter nearby. Its size hides it. Its gravity and magnetism reveal it. This contrast explains why neutron stars could be predicted before they were easily observed. Theory could follow the logic of collapse, but observation had to wait for signals strong or distinctive enough to overcome the problem of seeing something so small across interstellar distance. A neutron star's dimensions are also linked to its birth. The remnant becomes city-sized because collapse has removed the wider layers of the star and compacted the core until nuclear forces begin to resist. The expelled outer material becomes the supernova remnant, spreading outward across light years, while the core remains a small, dense center. The parent star's body becomes diffuse and luminous over a large region, while the parent star's core becomes almost impossibly concentrated. One event produces both expansion and compression. The explosion sends some material outward into the galaxy, and the remnant gathers the deepest material inward into one of the smallest stellar objects that can still have a surface. That surface is important because it preserves the distinction between neutron stars and black holes. A black hole of similar mass would have an event horizon rather than a material surface. A neutron star, by contrast, has a boundary where matter exists under tremendous gravity and where radiation can still emerge. This surface may be hidden by magnetospheric activity, accreted gas, or the angle from which it is observed, but physically it remains central to the object's identity. It allows heat to escape. It allows crustal stresses to build. It allows falling matter to strike, spread, and radiate. It allows the star to be studied as a compact body rather than as a region from which light cannot return. The city-size scale is therefore not just smallness. It is smallness with a surface, smallness before disappearance, smallness balanced on the last visible side of gravitational collapse. A neutron star's power comes from that balance. It is not large enough to dominate by volume, as a giant star does, and not hidden enough to withdraw behind an event horizon. Instead, it occupies a narrow physical category where mass remains exposed in concentrated form. Every kilometre of radius matters. A slightly larger star of the same mass implies a different interior. A slightly smaller one leans closer to instability. The measurements are difficult, but their meaning is deep. They speak to whether matter at the centre is stiff, exotic, or near surrender. The object that appears at first as a compact remnant becomes a question posed in mass and radius. How much weight can nuclear matter bear? How small can a star become and still remain a star? The answer is not given by size alone. but the size is the doorway. The neutron star is a city with solar mass only as a first approximation. More precisely, it is a collapsed stellar core in which the universe has exchanged breadth for intensity, turning a once immense furnace into a compact sphere where every familiar measure is under pressure. Gravity near the surface of a neutron star does not behave like the gravity known from planets, moons, or ordinary stars. It is still the same force, described by the same broad laws, but the compactness of the object pushes those laws into a more severe form. A mass greater than the Sun is gathered into a sphere only a few tens of kilometers wide, and that means the surface lies astonishingly close to the center of gravity. Distance matters. On Earth, the planet's mass is spread through a sphere thousands of kilometers across, and the surface is far enough from the center that gravity allows a familiar world to exist. Air can rise into a layered atmosphere. Mountains can remain standing. Oceans can shift without being crushed flat. A neutron star has no such patience. Its surface gravity is so intense that any ordinary landscape is forced into submission, and any loose matter is pulled downward with a force that makes height itself almost impossible. The star may have a crust, but the meaning of surface has changed. It is not a place where matter rests gently under an open sky. It is the outer boundary of a compact gravitational well, a narrow shell where every particle is held with enormous force against the deeper mass beneath it. This has consequences before anything even touches the star. An object falling toward a neutron star would not experience gravity as a simple downward pull. The side closer to the star would be pulled more strongly than the side farther away, creating tidal forces that stretch and distort the object. Around a planet, tides can raise oceans. Near a neutron star, tides can tear matter apart. A loose asteroid, a stream of gas, or the outer layers of a companion star may be elongated, heated, and stripped before reaching the surface. The star's gravity does not merely attract matter, it reorganizes matter's path, speed, shape, and final state. Falling material gains energy rapidly as it descends, and when it strikes the surface, the energy can be released as intense radiation. This is why some neutron stars become bright in X-rays when they feed from nearby companions. The surface is small, but the gravitational energy available to infalling matter is immense, because the matter has fallen into one of the deepest wells that can still end at a material boundary, rather than an event horizon. The atmosphere of a neutron star, if present, is not an atmosphere in the familiar sense. On Earth, an atmosphere is thick enough to contain weather, clouds, winds, and gradual changes in pressure with altitude. Around a neutron star, gravity presses gas into an extremely thin layer. The atmosphere may be only a shallow skin above the crust, held tight by gravity and shaped by magnetic fields. Even a small amount of gas can become important, because it controls the radiation that escapes from the surface and carries information about temperature, composition, and gravity. Yet the layer is so compressed that it cannot be imagined as a gentle envelope. It is closer to a film, pressed down against a star whose pull leaves little room for vertical structure. This thinness matters for observation. Light leaving the surface passes through the atmosphere, is modified by its particles, then climbs outward through curved space-time. By the time that light reaches a telescope, it carries both the imprint of surface conditions and the mark of the gravity it had to escape. Gravity also bends the path of light itself. Near a neutron star, the curvature of space-time is strong enough that radiation emitted from the far side can be redirected toward an observer who would not normally expect to see it. The star can reveal more of its surface than a simple sphere in flat space would allow. In less compact objects, the horizon is mainly geometric, only the hemisphere facing the observer is visible. In a neutron star, gravitational bending weakens that familiar boundary. Light from regions near the limb, and sometimes beyond it, can curve outward and arrive at distant instruments. This effect changes the shape of observed pulses. If a hot spot on the surface rotates into and out of view, the brightness does not rise and fall as sharply as it would without light bending, because gravity keeps part of the spot visible for longer. The star's gravity therefore writes itself into the rhythm of the light. A pulse is not only a sign of rotation, it is also a signal filtered through curved space-time. The energy of escaping light is changed as well. A photon leaving the surface must climb away from the neutron star's gravitational field. As it climbs, it loses energy, and its wavelength is stretched. This effect is called gravitational redshift. It is not caused by motion through space, but by the difference between the deep gravitational region where the photon began and the weaker region where it is later detected. Measuring that redshift can help reveal how compact the star is, because stronger surface gravity produces a larger shift. The challenge is that neutron stars are not simple lamps. Their spectra can be affected by magnetic fields, surface composition, temperature patterns, rotation, and surrounding plasma. Still, the principle remains powerful. Light is altered by the effort of escape, and that alteration becomes one of the few ways to estimate the relationship between the star's mass and radius. The gravity near the surface makes every escaping signal a messenger carrying evidence of the compact object it left behind. The same compactness sets the escape speed. On Earth, a rocket must reach a high speed to leave the planet permanently, but the requirement remains within the reach of chemical engines and careful engineering. From a neutron star, the required speed becomes a significant fraction of the speed of light. Nothing made from ordinary matter could launch from such a surface in any familiar way. The gravitational binding is too strong. A particle, a rock, or a spacecraft would need an extraordinary amount of energy to avoid falling back. Matter may arrive easily, drawn in by the pull, but leaving is difficult. The star is not a black hole, because light can still escape from outside its surface, but escape is not free. Every photon is weakened. Every particle must pay a large energy cost. The surface sits just on the visible side of gravitational captivity. That visible side is important because it gives neutron stars a kind of directness black holes do not have. A black hole has no material surface outside the event horizon. Matter falling into it may radiate from an accretion disk before disappearing, but once it crosses the horizon, no light returns. A neutron star can be struck. Gas can hit the surface, spread, heat, flare, and radiate. Thermonuclear burning can occur in accumulated layers when matter from a companion star piles up under pressure. The surface can produce bursts that reveal the star's gravity and radius indirectly. In these systems, the neutron star is not only a source of attraction, it is a wall at the bottom of a deep well. That wall changes the fate of infalling material, turning impact and compression into radiation that can be observed across the galaxy. Gravity also governs the shape of the star. Rapid rotation tries to flatten the object slightly, widening it at the equator, while gravity works to keep it compact. The result depends on spin, mass, and the stiffness of the dense matter inside. Even when the star rotates hundreds of times per second, its gravity remains strong enough to prevent it from flying apart under ordinary conditions. There is a limit. However, if a neutron star spins too quickly, matter at the equator would no longer remain bound in the same way. This breakup threshold is another route by which observations can constrain dense matter. A fast-spinning neutron star that remains stable tells something about its radius and internal structure, because a larger or softer star would respond differently to rapid rotation. Again, gravity near the surface is not just an environmental feature, it is part of the diagnostic language by which the object can be understood. In the quietest sense, the surface gravity of a neutron star changes the meaning of closeness. On Earth, being near a massive object can mean standing beside a mountain or orbiting a planet. Near a neutron star, closeness means entering a region where the geometry of space, the energy of light, the motion of gas, and the strength of matter are all under command from a compact mass. The star does not need to be large to dominate its neighborhood. Its influence comes from concentration. The surface is small, but around it the rules of escape, visibility, and impact are transformed. This is why the study of neutron stars often returns to gravity before any other property. Their magnetism can be extraordinary, their spin can be rapid, and their crust can be almost unimaginably strong. But gravity is the condition that holds all of it in place. It pulls the atmosphere into a skin, bends light into curved paths, turns falling matter into radiation, and keeps a solar mass exposed at a radius where ordinary matter would have failed long before. The next layer of the story lies directly beneath that severe boundary, in the crust where compression has not erased structure entirely, but has remade it into something stranger than stone and stronger than almost anything else in the known universe. The crust of a neutron star begins where the object is still just recognizable as a body with a surface. Yet nothing about that surface behaves like the ground of a planet. It is not a crust made by cooling lava, shifting plates, sediment, water, or weather. It is the compressed outer skin of a collapsed stellar core, a layer forced into existence by gravity and held against the star with such strength that ordinary ideas of hardness become too small. Above it, any atmosphere is only a thin film. Beneath it, matter descends towards stranger and less certain states. The crust lies between those two regions, neither familiar nor fully unknown, and because it still contains arranged nuclei, it offers one of the few layers of a neutron star where structure can be described with some confidence. At the very top, the material is thought to be rich in iron, the ash of the star's final nuclear history and the last stable endpoint of many fusion paths before collapse. These iron nuclei are not spread through a loose solid as they would be in ordinary metal. They are packed into an extreme lattice, squeezed by gravity until the electrons around them are forced into highly energetic states. The result is sometimes called a solid, but even that word has to be used gently. It does not mean a solid that could be chipped, handled, melted in a furnace, or laid out on a table. It means matter with a rigid, ordered arrangement, pressed so tightly that the strength of the surface exceeds nearly every material known from everyday physics. The crust is thin compared with the star as a whole, perhaps only around a kilometre deep in many models, but that thinness does not make it weak. A layer can be shallow and still carry extraordinary force when it's pinned to a body this compact. On Earth, mountains rise because rock can support uneven loads for long periods, though erosion and gravity keep remaking them. On a neutron star, the surface gravity is so severe that high mountains are impossible. The crust may hold tiny irregularities, sometimes described as star mountains, but these features would likely rise only by small fractions of a millimetre, or perhaps a few millimetres in many estimates, depending on the strength of the crust and the rotation of the star. Such heights sound insignificant until the gravity is remembered. A tiny bump on a neutron star can represent enormous stress. The mass involved may be large, and the distortion can influence how the star radiates, or how it sends weak ripples through space-time if the asymmetry persists while the star spins. A mountain too small to see by ordinary intuition can still matter because the star beneath it is so dense. Surface shape, in this environment, is measured not by grandeur but by resistance. The crust resists flattening only because nuclear matter can bear immense strain before it yields, deeper in the crust. The pressure grows and the composition changes. Electrons are squeezed into nuclei, making them more neutron-rich. At a certain depth, some neutrons are no longer bound inside nuclei at all. They begin to drip out, forming a strange mixture of neutron-rich nuclei surrounded by a sea of free neutrons. This region is called the inner crust, and it is one of the places where the language of ordinary matter becomes especially strained. The nuclei remain, but they are embedded in conditions that have no close counterpart in common experience. The free neutrons may flow with very little resistance, forming a superfluid, a state in which a substance can move without ordinary viscosity. That possibility matters because it may help explain sudden changes in the rotation of some pulsars. These changes, known as glitches, occur when a pulsar that has been gradually slowing suddenly spins a little faster. One explanation is that the crust and the superfluid interior do not always rotate together perfectly. Stress builds as the outer part loses rotational energy, and then angular momentum is transferred from the superfluid region to the crust. The shift is small by stellar standards, but it is measurable across interstellar distances through the timing of pulses. In that way, the crust becomes more than a static shell. It becomes part of a hidden mechanical system, storing strain, slipping, coupling to deeper layers, and revealing its motion through the rhythm of a rotating star. Farther down, as density increases still more, nuclei may lose their ordinary roughly spherical shape. The competition between nuclear attraction, electric repulsion, and pressure can stretch nuclear matter into rods, slabs, tubes, and other complex forms. Physicists have given these phases the informal name nuclear pasta, because their shapes can resemble strands, sheets, and hollow structures. The name is light, but the matter it describes is not. Simulations suggest that these arrangements may be among the strongest materials in the universe, because they are held together by nuclear forces across enormous densities. Near the bottom of the crust, matter may become a tangled, elastic phase, where the boundary between nuclei and surrounding neutron sea begins to blur. This region could influence how heat moves through the star, how magnetic stresses are transmitted, and how the crust fractures under strain. The crust strength is especially important in magnetars, the highly magnetized relatives of ordinary neutron stars. In a magnetar, the magnetic field can be so intense that it twists and stresses the crust from within and above. The crust may resist for a time, storing energy like an overstrained shell. Then, if the stress exceeds what the material can bear, the crust may crack or shift. This event is often called a starquake. Though it is not an earthquake in the planetary sense, there are no tectonic plates drifting over a molten mantle. Instead, there is a compact crust responding to magnetic force under gravity so strong that even a small rearrangement can release tremendous energy. Such fractures are thought to help power bursts of high-energy radiation from magnetars. The surface breaks not because it is fragile, but because the forces acting upon it are even stronger than its remarkable strength. That distinction matters. The crust of a neutron star is not weak rock shattered by violence. It is extreme matter pushed past its limit by extreme magnetism, rotation, cooling, or internal motion. Cooling also shapes the crust over time. A newborn neutron star is hot, but it sheds energy through neutrinos and radiation. As the surface cools, the outer layers settle and solidify in the sense allowed by their conditions. The cooling is not just a fading of heat, It changes how the crust conducts energy, how it couples to the magnetic field, and how the star appears in X-rays. If matter from a companion later falls onto the surface, it can bury older magnetic fields, heat the crust, trigger nuclear reactions in the accumulated material, and alter the outer composition. In accreting neutron stars, the crust may be continually rebuilt. Fresh hydrogen and helium from a companion can settle, burn, and be compressed into heavier ashes as more material arrives. Over time, that buried material is pushed deeper, where pressure drives further nuclear reactions. The crust becomes a record not only of the original supernova, but of later feeding, each layer changed by compression as it sinks toward denser regions. The hardness of the crust is also tied to the question of gravitational waves. If a rotating neutron star is not perfectly symmetrical, it may emit continuous gravitational radiation, though such signals are extremely difficult to detect. The possible size of any asymmetry depends partly on how much strain the crust can support before breaking. A stronger crust can hold a larger distortion, a weaker one would relax more quickly. Even a minute unevenness becomes significant because the star spins so rapidly and contains so much mass. The crust therefore connects microscopic nuclear strength to astronomical signals that may someday be measured by instruments designed to detect tiny changes in spacetime. It is a bridge between the behavior of particles and the motion of a compact star. The surface shell that once seemed like a boundary becomes an active participant in observation. Its thickness, elasticity, composition, and failures all leave traces. It shapes thermal emission. It may help produce glitches. It can fracture under magnetic stress. It can be reheated by accretion. It may support small distortions that matter far beyond their height. The crust is where a neutron star still has something like geology. But it's geology translated into nuclear density. There are no rivers, no continents, no weathering slopes, and no soil. There is instead a rigid skin of compressed nuclei and free particles, carrying stresses that would erase any ordinary material. The deeper the crust goes, the less clearly it belongs to the surface, and the more it becomes an introduction to the hidden interior. At its lower edge, nuclei may dissolve into a more uniform fluid of dense matter, and the confidence of models begins to thin. The crust gives the neutron star its outer strength, but it also marks the last layer before the object becomes harder to describe. Above it lies radiation and magnetic structure. Within it lies the strongest solid-like matter known. Beneath it waits the uncertain core, where pressure may change not only the arrangement of matter, but the identity of the particles themselves. The hidden interior of a neutron star begins where the crust loses its last clear structure, and matter passes into a realm that cannot be opened, sampled, or recreated on Earth. Above this boundary, there are still nuclei, even if they are stretched, pressed, and surrounded by free neutrons. Below it, the pressure becomes so high that nuclei may dissolve into a more continuous form of dense matter. The star still has layers, but they are no longer layers in the planetary sense. They are changes in density, particle behavior, and force, moving inward through a sphere whose radius is small, but whose physical depth is immense. The deeper region is often called the core, yet the word can sound too simple. In a living star, the core is where fusion happens. In a neutron star, the core is where fusion has already failed, where collapse has already remade matter, and where the remaining question is how long matter can keep resisting gravity before it crosses into something even less visible. This interior is one of the most important unknown environments in modern astrophysics, because it joins the largest and smallest scales in a single object. Gravity supplies the pressure. Nuclear physics supplies the resistance. Quantum rules decide which particles can occupy which states. Observation supplies only indirect signs, gathered from radiation, timing, cooling, and the behavior of stars that merge or feed from companions. The result is a scientific problem that is both concrete and inaccessible. A neutron star has mass, it has radius, it has surface emission, it can spin and slow down, it can glitch, it can collide. Yet the arrangement of matter at its deepest centre remains hidden behind the very density that makes the object valuable to study. No telescope can look through the surface and watch the particles inside. The only way to approach the core is to listen to what the whole star does and ask what kind of matter would allow that behaviour. The outer core is usually imagined as a dense fluid dominated by neutrons, with a smaller number of protons, electrons, and perhaps other particles mixed in to maintain charge balance and stability. The neutrons may form a superfluid, moving in a state where ordinary friction becomes almost absent. The protons may form a superconducting component, carrying magnetic behaviour in a way unlike ordinary metal. These states are not speculative in the broad sense, because superfluidity and superconductivity are known phenomena in physics, but their neutron star versions occur under pressures and densities far beyond laboratory materials. The interior may therefore be smooth in one sense and highly complex in another. It may contain distinct fluids that interpenetrate, rotate imperfectly together, store angular momentum, and interact with magnetic fields. This hidden motion may be part of what causes pulsar glitches. The crust turns with the observable star, but a superfluid inside may lag behind or move differently. When the coupling changes, a small amount of angular momentum can be transferred outward, and the pulse rate changes. A distant radio signal, arriving with almost clock-like regularity, becomes the surface expression of an invisible rearrangement deep below. Cooling offers another clue. Young neutron stars lose heat through neutrino emission from the interior and through radiation from the surface. The rate of cooling depends on which particles are present and what reactions they allow. Some processes release neutrinos efficiently, making the star cool faster. Others are slower, leaving the star warmer for longer. By measuring the temperature of neutron stars of different ages, astronomers can compare observations with models of internal matter. The difficulty is that age, surface composition, magnetic fields, and past accretion can all complicate the reading. A cool star may have an efficient neutrino process inside, or it may have a different history than expected. A warmer star may suggest slower cooling, or it may have been reheated. The core does not announce its contents plainly. It leaves a pattern that must be separated from every other influence shaping the star. One of the deepest questions is whether the central density becomes high enough to create particles beyond neutrons and protons. In ordinary atomic nuclei, protons and neutrons are built from quarks, smaller constituents bound together by the strong force. Under extreme pressure, some theories suggest that these particles could lose their individual boundaries, producing a form of quark matter. Other models allow heavier particles called hyperons to appear, or suggest that meson condensates may form. These names can sound exotic, but the underlying issue is direct. When matter is squeezed hard enough, nature may find a lower energy arrangement by changing which particles are present. The star may not remain simply a ball of neutrons. Its centre could contain phases of matter that are familiar only through theory and high-energy experiments, translated into a cold, dense astronomical setting. None of these possibilities can be treated as settled. They are candidates for what the core might become, not conclusions forced by present evidence. This uncertainty is captured in the equation of state, the relation between pressure and density inside the star. If the equation of state is stiff, matter resists compression strongly. and neutron stars can support larger radii and higher maximum masses. If it is soft, matter compresses more easily, and the star becomes smaller or collapses at a lower mass. Observations of massive neutron stars already rule out some soft possibilities, because any acceptable model must allow those stars to exist without becoming black holes. Measurements from X-ray observatories, pulse profiles, and gravitational wave events further narrow the range. When two neutron stars spiral together and merge, their tidal distortion before collision depends on how easily each star is deformed by the other's gravity. A larger, softer, or stiffer interior leaves a different imprint on the gravitational wave signal. In this way, the hidden core can be studied not only through light, but through the motion of space-time itself during the final moments of a binary system. The core also determines the maximum mass a neutron star can bear. This limit is not known exactly, because it depends on the true behavior of dense matter. A non-rotating neutron star above that limit cannot remain stable. It must collapse into a black hole. Rotation can temporarily support extra mass, and heat or differential rotation after a merger can delay collapse for a short time. But those supports fade. The final decision belongs to the interior. If pressure can answer gravity, a remnant survives. If not, the surface disappears behind an event horizon. This makes the core a threshold hidden inside another threshold. The star has already survived the collapse that created it, but its deepest matter still carries the question of whether survival can continue. A neutron star near the maximum mass is not merely heavier. It is closer to losing the category that defines it. Even the magnetic field may be rooted partly in the hidden interior. The field observed outside the star threads through the crust and magnetosphere, but its long-term evolution may depend on currents and superconducting regions below the surface. In magnetars, where the field is especially intense, stresses may move through the crust from deeper magnetic structures. If the interior superconducts, magnetic flux may be arranged in narrow tubes, interacting with superfluid vortices tied to rotation. What happens beneath the crust can shape what is seen far above it bursts, timing irregularities, thermal patterns, and the gradual aging of the magnetic field. The core is not simply a hidden reservoir, it is a controlling system whose effects reach the surface through motion, heat, and magnetism. That is what makes neutron stars so valuable and so elusive. They are compact laboratories sealed by gravity. Every observed property is a partial experiment. A pulse profile asks how compact the star is. A cooling curve asks which particles move inside. A glitch asks how the crust couples to a superfluid. A merger asks how the entire object deforms under tidal stress. A high mass measurement asks how much weight dense matter can bear. None of these questions alone reveals the core completely, but together they build a narrowing corridor of possibility. The hidden interior remains hidden, yet not silent. It speaks through consequences, and each consequence removes some worlds from the list of possible interiors while leaving others alive. The calm difficulty is that the deepest truth may not be a single simple state. A neutron star core could change with depth, mass, age, magnetic field, and rotation. A lighter star may contain mostly nucleonic matter, while a heavier one may approach more exotic phases at the center. Two neutron stars with similar surfaces may hold different interiors because one lies closer to the stability limit. The category neutron star may therefore include a family of hidden structures rather than one universal design. From the outside, they are compact remnants. Inside, they may be layered answers to the same pressure, each answer chosen by mass and history. The crust showed that matter could become stronger than ordinary solidity. The core shows that strength alone is not the final issue. At the center, the question becomes identity. What particles remain? What phases appear? What pressure is enough? The neutron star holds these questions under its surface, not as abstract puzzles, but as the physical reason it exists at all. Beneath the crust, gravity is still asking for collapse, and matter is still answering in the only language available to it: resistance, transformation, and the narrow endurance of a star that has not yet vanished. Spinning stellar remnants reveal one of the strangest forms of conservation in the universe. A star can die, collapse, and lose most of its visible body, yet still keep the memory of its rotation. Before the collapse, the massive star is enormous, and its core may turn slowly compared with what comes later. The material occupies a wide volume, so its angular momentum is spread across a broad radius. When the core contracts into a neutron star, that radius shrinks with almost unbelievable severity. The same rotational inheritance is gathered into a much smaller space, and the spin rate rises. The familiar comparison is a skater drawing in the arms, but in a neutron star the scale is much more extreme. A stellar core that once occupied a region far larger than Earth becomes a compact sphere only tens of kilometers wide, and the act of shrinking turns ordinary rotation into a defining physical power. The newborn remnant may spin many times each second, not because something has wound it up after death, but because collapse has concentrated motion as surely as it concentrated mass. This rotation matters because a neutron star is not a smooth passive ember. It is dense, magnetic, hot, and surrounded by charged particles. And when such an object spins, the space around it becomes organized by that motion. Magnetic field lines tied to the star sweep through the surrounding plasma. Electric fields arise. Particles can be accelerated to high energies. Radiation may be guided into beams that do not necessarily align with the rotation axis. If those beams cross Earth, the star appears to pulse, not because it is turning on and off, but because its lighthouse-like beam repeatedly sweeps across the same line of sight. Rotation transforms a compact remnant into a precise signal. Without spin, many neutron stars would be far harder to find. With spin, they become clocks, beacons, engines, and laboratories for gravity and dense matter. The earlier spin of a neutron star depends on the parent core, the collapse, the magnetic field, and the asymmetry of the supernova. Some are born relatively slow, others are born turning rapidly enough that their surfaces move at a significant fraction of light speed near the equator. Yet even rapid birth is not the end of the story. A rotating neutron star loses energy over time. The magnetic field and surrounding particles carry rotational energy away, and the star gradually spins down. Its pulses, if observed across long intervals, arrive slightly later than they would from a perfectly unchanging clock. This slowing is tiny from one rotation to the next, but over years, centuries, and longer spans, it records the aging of the remnant. A young pulsar often spins quickly and loses energy strongly, feeding a surrounding nebula or producing energetic radiation. An older isolated pulsar may slow until its beams weaken, or no longer produce the same detectable emission. The star does not stop being a neutron star, but it may become quiet to telescopes that once could have heard it. The slowing of rotation is partly a form of power. As the star spins down, energy leaves the rotation and enters the magnetosphere, the region controlled by the magnetic field. Charged particles can be pulled from the surface or created in cascades, then accelerated along magnetic structures. The details are complex, and different models explain different parts of pulsar emission. But the broad idea is steady: the neutron star's rotation and magnetism work together to create observable radiation. This is why a pulsar is sometimes described as rotation-powered. It does not shine primarily because fusion continues in its core. Fusion is over. The object shines and pulses because its rotational energy is being drained through electromagnetic processes. The dead star is slowly spending the motion it inherited from collapse. That spending can be measured with remarkable precision. Pulsars are timed by recording the arrival of each pulse, then comparing those arrivals with a model of the star's spin, position, and motion. Some pulsars are so stable that they rival the best clocks over long intervals, though they are not perfect. Their timing reveals gradual slowdown, sudden glitches, orbital motion if they have companions, and sometimes the presence of planets. In this sense, rotation becomes a language. A change in pulse timing can indicate matter inside the star shifting, a companion tugging gravitationally, or gravitational waves carrying energy away from a binary system. The remnant spin is not simply a property. It is the moving hand on an astronomical instrument. Every pulse is a mark from a compact object whose surface cannot be resolved directly, yet whose rhythm can be followed with astonishing care. The most sudden changes are glitches. A pulsar that has been slowing gradually may suddenly rotate a little faster, then begin slowing again. The change is small, but the timing is precise enough for the jump to stand out clearly. Glitches suggest that the neutron star is not rotating as one perfectly rigid body. The crust and the superfluid interior may exchange angular momentum after stress builds between them. In one picture, tiny vortices in the superfluid interior become pinned to the crust or in a lattice, preventing the superfluid from adjusting smoothly as the crust slows. When enough stress accumulates, many vortices shift, and angular momentum moves outward. The crust spins up slightly, and the pulse timing changes. A distant observer sees only a small irregularity in a radio signal. But inside the star, the event may represent a deep rearrangement between layers of matter unlike anything on Earth. Rotation also interacts with shape. A neutron star that spins rapidly is not perfectly spherical. Centrifugal effects make it slightly wider at the equator, though gravity keeps the distortion limited. The faster the spin, the more the star tests the strength of its own gravity and the stiffness of its interior. There is a maximum possible spin rate beyond which material at the equator could no longer remain bound. Observed spin rates therefore place limits on the star's radius and internal matter. If a neutron star is found rotating extremely fast without breaking apart, its existence implies that the compact object is small enough, dense enough, and internally strong enough to survive that rotation. Once again, spin becomes a probe of matter that cannot be sampled. The fastest known pulsars are not usually newborn objects. Many belong to binary systems and have been spun up later in life by accretion. This creates a second life for some neutron stars. An old remnant that has slowed over time can orbit a companion star closely enough to pull material from it. As gas spirals inward, it carries angular momentum. Some of that angular momentum is transferred to the neutron star, making it rotate faster. Over long periods, the old star can be recycled into a millisecond pulsar, spinning hundreds of times each second with great stability. The word recycled is unusually fitting. The neutron star has not become young again in its interior, but its rotation has been renewed by feeding from another star. A binary system can therefore take a quiet remnant and return it to visibility. Accretion does not only change the spin, it can heat the surface, bury or modify magnetic fields, trigger bursts, and create disks that shine in X-rays. The interaction between the infalling matter and the rotating magnetosphere determines whether material reaches the surface easily or is flung away. If the magnetic field rotates quickly enough, it may act like a propeller, preventing some matter from accreting, if conditions shift. The same system may alternate between feeding and expelling. The neutron star becomes an engine whose behavior depends on the balance between gravity pulling matter inward, rotation sweeping magnetic fields around, and plasma trying to find a path through that moving structure. This complexity shows why spin cannot be separated from environment. An isolated neutron star spins down in one way. A neutron star in a binary can be spun up, slowed, obscured, reheated, or changed by the companion it feeds upon. Rotation also gives neutron stars a role in testing relativity. In tight binary systems, the timing of pulses can reveal orbital decay, gravitational time delay, and the effects of curved space-time. When two compact objects orbit one another, energy can leave as gravitational waves, causing the orbit to shrink. Pulsar timing can measure this shrinkage long before a merger occurs. The rotating neutron star becomes a clock carried through strong gravity, and the regular pulses allow astronomers to watch the orbit change with extraordinary sensitivity. A dead core, rotating in darkness, can test the structure of space-time. The life of a spinning neutron star is therefore not a simple slowing from fast to still. It can begin rapidly, lose energy, glitch, interact with fields, enter a binary, feed from a companion, accelerate into millisecond rotation, or eventually quiet down again. Spin is both inheritance and history. It records the collapse that made the star, the magnetic field that drains it, the crust and interior that exchange angular momentum, and the companions that may later revive it. The remnant turns because it once was larger, and because physics preserves motion even through catastrophe. As long as it turns, it can make itself known. The next form of that known presence is the pulse itself, the repeating signal that first made neutron stars impossible to dismiss and turned a compact corpse of stellar matter into one of the most precise natural clocks in the galaxy. Pulsars made neutron stars visible not as tiny disks in a telescope, but as rhythm. The first unmistakable signals did not look like the steady glow of a star or the smeared light of a nebula. They arrived as repeated radio flashes, separated by intervals so regular that the pattern seemed almost artificial. This precision was the clue that changed the status of neutron stars from theoretical remnants to observed objects. A small body spinning quickly, carrying a strong magnetic field, could sweep beams of radiation through space. If Earth happened to lie in the path of one of those beams, radio instruments would not see the whole star turning. They would register a pulse, then another, each one marking a rotation of the hidden remnant. The star itself was not blinking. The geometry was doing the blinking for it. A pulsar is therefore a neutron star seen from a fortunate angle, though fortunate is only a matter of alignment, not comfort. The radiation that makes the pulse is produced in the magnetosphere, where the magnetic field controls the motion of charged particles around the star. Because the magnetic axis is usually tilted away from the rotation axis, the beams do not remain fixed in one direction. They sweep around as the star turns, attached to a compact object whose surface gravity and magnetic field are both extreme. When one beam crosses Earth, the signal appears with a regularity that can exceed almost any ordinary astronomical cycle. The word pulsar preserves that appearance, but the deeper meaning is rotation. The pulse is a clock face made from radiation, and the rotating neutron star is the clockwork beneath it. The discovery of pulsars in the late 1960s was startling because the signals were too exact to fit comfortably into earlier expectations. Jocelyn Bell Burnell, working with Anthony Hewish and a radio telescope designed to study compact radio sources, noticed a repeating signal that returned at a steady interval. Its regularity was so strange that it was briefly given the informal label little green men. Not because aliens were the favoured explanation, but because the signal seemed difficult to place. The interpretation soon changed. Other sources were found. Their distribution across the sky and their pulse properties pointed to a natural population, not an artificial transmitter. The best explanation became a rotating neutron star, exactly the kind of compact remnant that earlier theory had suggested might follow a supernova. The alien possibility faded, but the actual object was hardly less remarkable. Nature had made something small, dense, rotating, and precise enough to imitate intention without needing any intention at all. The reason pulsars can act as clocks lies partly in their enormous inertia. A neutron star contains so much mass in such a compact body that its rotation cannot be easily disturbed. Each turn carries the momentum of a collapsed stellar core. The star gradually loses rotational energy, so the pulses slowly drift as the spin declines. But this slowdown can be measured and modelled. Once the change is understood, many pulsars become extraordinarily predictable. The arrival time of each pulse can be compared against a timing model, revealing not only the star's rotation, but also its motion through space, the effect of any companion, and subtle changes in the environment between the star and Earth. What begins as a flash becomes a measurement of astonishing range. A pulsar does not merely announce that a neutron star exists. It can reveal where it is, how fast it spins, how quickly it slows, whether it orbits another object, and whether its interior has shifted. This precision is strongest in millisecond pulsars, many of which have been spun up through accretion in binary systems. A collection of such pulsars spread across the sky can be used as a vast timing array. If a passing gravitational wave slightly stretches and compresses the space between Earth and those pulsars, the arrival times of their pulses may shift in a correlated pattern. No single pulse announces the wave loudly. Instead, many clocks must be watched together, and the evidence grows from tiny timing differences across large spans of space. In this way, neutron stars become detectors for movements of space-time far larger than themselves. Pulsar timing also helped confirm one of the important predictions of general relativity. In a binary system containing a pulsar and another compact object, the orbit can slowly shrink as energy is carried away by gravitational waves. The pulse arrivals reveal the changing orbit with remarkable accuracy, because the pulsar acts like a clock moving through a gravitational field. When the pulse arrives early or late, the difference can encode orbital motion, time dilation, and the curvature of space-time around the system. The star's rhythm becomes a probe of gravity itself, a dead core. Only a small remnant of a massive star can test the behaviour of the universe on scales far beyond its own surface. The pulse is also shaped by the star's surroundings. Radio waves do not travel through the galaxy untouched. They pass through ionized gas, magnetic fields, and dust-filled regions between stars. Different radio frequencies can be delayed by different amounts as they cross this material, producing a measurable dispersion. By studying that delay, astronomers can estimate how much ionized matter lies along the path. The pulsar becomes not only a clock but also a lamp shining through the interstellar medium. Its signal carries information about the space between stars, even before it reveals the star itself. Not all pulsars behave perfectly. Some show glitches, sudden jumps in spin that point toward internal rearrangements. Others show timing noise, small irregularities that may come from magnetospheric changes, crustal processes, or less understood internal motion. Some pulsars switch between different emission states, as though the magnetosphere has reorganized into a new pattern. These irregularities do not make pulsars less valuable. They make them more revealing. Perfect regularity would show rotation alone. Imperfection shows structure. A glitch hints at superfluid matter beneath the crust. A change in pulse shape may suggest altered particle flows above the surface. A long-term timing drift may reveal a companion or a planet. The pulse train is therefore not a single simple beat. It is a layered record of rotation, magnetism, interior physics, and environment. The beams themselves are still not fully understood in every detail. Charged particles are accelerated along magnetic field lines. Radiation is produced, and the geometry of the emission region shapes what reaches Earth. Some pulsars are bright in radio. Others are seen in X-rays or gamma rays. Some young pulsars power surrounding nebulae, filling them with energetic particles and radiation. Older millisecond pulsars may be quieter in appearance, but more precise in timing. The class is unified by rotation and neutron star compactness, yet it contains many kinds of behavior. A pulsar is not one simple machine repeated across the galaxy. It is a family of compact engines, each shaped by age, magnetic field, spin, history, and surroundings. Their value as cosmic clocks depends on a balance between steadiness and change. They are steady enough to measure with extreme precision, but not so steady that they become featureless. Each deviation matters because the baseline is so regular. A slight delay, a sudden spin change, a gradual orbital shift, or a frequency-dependent distortion can all become evidence. This is why pulsar astronomy often feels like listening rather than looking. The star is too small to resolve, too distant to touch, and too extreme to interpret through direct analogy. Yet its rotating beam arrives again and again, carrying timing marks across hundreds or thousands of light years. The repetition gives observers a handle on an object otherwise hidden by scale. What was once a collapsed core becomes a metronome for the galaxy. Still, a pulsar is not eternal. As rotational energy is lost, the beams may weaken or cease to cross the conditions needed for strong emission. The star can move across a kind of death line, becoming radio quiet even while the neutron star remains. Others may be revived by accretion, spun into millisecond life by a companion that donates matter and angular momentum. The clock can fade. The clock can be reset. The clock can be hidden by geometry, so that many neutron stars may pulse in directions that never touch Earth. The observed population is only the aligned fraction of a larger invisible population. That limitation gives each detection a double meaning. Every pulsar found is both an object in itself and a reminder of many others that may be turning silently from our point of view. The discovery of pulsars transformed neutron stars because it gave collapse a rhythm that could be measured. Theory had imagined dense remnants. Supernova remnants had hinted at compact survivors. Pulses made the case audible in data, steady enough to follow and strange enough to demand explanation. They turned neutron stars into clocks, gravitational probes, maps of interstellar matter, tests of dense interiors, and beacons in the dark structure of the Milky Way. The beam that sweeps past Earth is narrow, but the meaning it carries is wide. In that repeated flash, a dead star does not simply shine. It counts its own rotation, reveals its hidden stresses, and marks a position in the galaxy with a precision that would later invite an even stranger use navigation by remnants, and maps written not with landmarks of stone, but with pulses from collapsed stars. The idea of mapping a civilization by pulses begins with a quiet assumption. Some natural signals are stable enough to outlast the people who first measured them. A mountain range can erode, a shoreline can shift, and a star can move across the galaxy. But the pulse of a rotating neutron star may remain regular over spans long enough to tempt another kind of use. Once pulsars were understood as compact remnants rather than artificial transmissions, their precision suggested more than observation. They could become reference points. Their pulses could mark positions in a galaxy, where ordinary landmarks are separated by unimaginable distances and where nearly every object is in motion. A pulsar is not fixed in the deepest sense, but it can be timed. Its rotation can be measured, its gradual slowdown can be modelled, and its location on the sky can be compared with others. For a species trying to describe where one small planet sits among hundreds of billions of stars, that kind of regularity carries a special attraction. Pulsars offered something stranger and more exact than constellations or bright stars, clocks scattered through the Milky Way. That idea reached one of its most famous forms on the golden record carried by the Voyager spacecraft. The record was not only a collection of sounds, images, and symbolic information. It also carried a diagram intended to place Earth within the galaxy by using pulsars as markers. Lines radiated from a central point representing the Sun, each line pointing toward a different pulsar, each carrying information about the pulsar's timing. The message relied on the notion that a technically capable civilization, finding the spacecraft far from Earth, might identify those pulsars by their periods and work backward to the region from which the probe had come. The map was an act of scientific imagination as much as engineering. It treated neutron stars not simply as objects of study, but as part of a galactic coordinate system, a way for a small world to leave directions in the dark. The elegance of the map comes from the fact that a pulsar period is not a casual feature. It is tied to the rotation of a compact star, and that rotation can be measured with great precision. A pulsar that turns in a fraction of a second, or in several seconds, produces a repeated signal that can be distinguished from many others. The periods are not perfectly eternal, because pulsars slow as they lose rotational energy, but the slowdown itself can often be measured. In principle, a pulse period and its rate of change can act like a timestamp as well as an identifier. The signal says not only which pulsar is being referenced, but something about when that measurement was made. A map based on pulsars does not need the pulsars to be absolutely unchanging. It needs their changes to be predictable enough that a future reader could account for them. Yet the calm beauty of the idea is accompanied by limitations. Pulsars are precise, but they are not immovable. They travel through the galaxy, often at high speeds because the supernova explosions that created them can give them strong kicks. Over long timescales, their positions change. Their beams may not always point in the same useful direction. Some pulsars become less active or cross into states where their radio emission fades. Others may be difficult to detect from a different location, because the beam that sweeps across Earth may not sweep across another world. A pulsar map assumes that the chosen beacons can still be found, identified, and interpreted by a reader who shares no context except the physics of rotating neutron stars. That assumption is not unreasonable, but it is not simple. It depends on astronomy, timing, geometry, and the survival of a small spacecraft across deep time. The Voyager probes themselves move slowly compared with stars and with the scale of the Milky Way. They have crossed into interstellar space, but they will not approach another star system for a very long time, and the chance of being found is extremely small. The map is therefore not a practical message in the ordinary sense. It is closer to a declaration of location, a carefully built sign attached to a bottle, released into an ocean whose currents are stellar motion. Its importance lies not in expectation, but in what it reveals about pulsars and about humanity's understanding of place. To draw such a map is to accept that Earth is not the centre of any natural coordinate grid. Its position must be described relationally, by reference to objects larger, older, and more stable than human history. Neutron stars, the collapsed remains of dead suns, became part of that description. There is a deep irony in using stellar corpses as markers for life. Pulsars are born from catastrophic endings. They are remnants of stars whose outer layers were torn apart and scattered into space, yet their aftermath produces one of the most orderly signals in astronomy. A supernova can create a clock, collapse can produce a beacon. The same process that destroys a star can leave behind a rhythm stable enough to help define a planet's address. This is not a contradiction so much as a pattern often found in astrophysics. Violent events can leave precise structures. Explosions can seed future systems with heavy elements. Catastrophe can become reference. The difficulty of reading such a map grows when the wider population of pulsars is considered. Only a fraction of neutron stars are observed as pulsars from Earth, because the beam has to cross the right line of sight, and the emission must be strong enough to detect. Many more neutron stars may exist unseen, either because their beams point elsewhere, because they are too old and quiet, or because their signals are hidden by distance and intervening matter. A future reader would not necessarily see the same pulsar sky that Earth sees. From another location in the galaxy, some familiar pulses might vanish while others appear. The map's chosen pulsars were selected because they were known and measurable from Earth at the time. That makes the diagram historically specific. It carries the astronomy of its era, not a perfect universal reference system. The record therefore preserves not only a location, but a moment in scientific knowledge. This does not make pulsar navigation obsolete. Spacecraft navigation can, in principle, use X-ray pulsars as natural timing sources. A spacecraft that measures pulse arrival times from several known pulsars could compare those times with predictions and estimate its position, somewhat like a deep space version of navigation by satellites, except the transmitters are collapsed stars rather than machines. The method is demanding because the signals are faint, the instruments must be sensitive, and timing must be accurate. Still, pulsars can serve as natural beacons because physics has made them regular. Their value lies in repetition. A rotating neutron star does not care who measures it, yet the pulse can still become a coordinate when a mind recognizes the pattern. The same idea changes the emotional scale of neutron stars. Earlier, they appeared as dense remnants, as crusts and cores and surfaces under impossible gravity. As pulsars, they became clocks. As map points, they become part of a larger act of orientation. Their power is no longer only destructive or exotic, it becomes directional. A neutron star can strip matter from a companion, bend light around itself, and emit high-energy radiation. But it can also provide a reference line in the dark. This gentler role does not soften the object itself. It only shows how the same physical extremity can be interpreted differently depending on the question asked. The beam can be radiation, clock, signal, and landmark at once. Nothing in the galaxy is truly still. Pulsars slow, stars orbit the galactic center, spiral arms shift, spacecraft drift. Records erode. Civilizations rise within intervals that are short beside stellar time. To place a map on a probe is not to defeat this motion, but to choose a set of references stable enough for meaning to survive a little longer. Neutron stars are suited to that role because they preserve the concentrated aftermath of collapse. Their rotation changes slowly enough to be useful. Their signals can cross great distances, and their identities can be encoded in timing. They are not perfect anchors. They are only better anchors than most. That distinction is important, because science often works through such imperfect stability. A pulsar is not eternal, but it is regular. A map is not guaranteed to be read, but it can still be made with care. In the end, maps written in pulses show a quieter side of neutron star power. The power is not only in gravity or density, but in reliability emerging from collapse. A dead star becomes a clock, and a clock becomes a landmark, and a landmark becomes a way of saying where a living world once sent a small machine outward. Yet the map also points toward a stronger truth beneath it. The pulse exists because rotation and magnetism are coupled around compact matter, and in some neutron stars that coupling grows far beyond ordinary pulsar behavior, when magnetic fields become the dominant fact of the remnant's life. The quiet clock gives way to a more strained and unstable object, one in which the crust itself can crack under magnetic force, and the star can release its power in sudden bursts. A magnetar is a neutron star in which the magnetic field becomes the defining fact of the object's life. Its mass and radius may not differ greatly from other neutron stars, and it may have formed through the same broad pathway of core collapse, but the field surrounding and threading it is pushed to an extraordinary level. In an ordinary pulsar, rotation and magnetism work together to guide charged particles and produce beams. In a magnetar, the magnetic field is so intense that it stores enough energy to dominate the surface, stress the crust, and power bursts of radiation long after the original supernova has faded. The star is still compact, still dense, still held at the edge between visible matter and deeper collapse, but its behavior is no longer governed mainly by the slow spending of rotational energy. The magnetic field itself becomes the reservoir. It bends the star's surroundings into a strained invisible architecture, and over time that architecture can twist, shift, and break. The numbers attached to magnetar fields are difficult to absorb, so their meaning is better approached through consequence. A magnetic field on Earth can guide a compass needle and shield the atmosphere from some charged particles arriving from the Sun. A neutron star field can already be billions or trillions of times stronger than that. A magnetar field can rise still further, reaching intensities where atoms would be distorted, where electron motion is constrained into narrow paths, and where empty space near the star is no longer a passive background. In such fields, quantum effects can influence how light travels, how particles move, and how radiation escapes. The field is not simply painted around the star, it is part of the physical environment, carrying energy, pressure, and stress. For a magnetar, magnetism is not a detail added to gravity, it is a second form of command, layered over the compactness that already makes neutron stars severe. The origin of such extreme fields remains an active question. One possibility is that the magnetic field of the collapsing stellar core is greatly amplified as the core shrinks, with field lines compressed into a much smaller volume. Another possibility involves a rapidly rotating newborn neutron star, whose internal motion briefly acts like a dynamo, strengthening the field soon after birth. The details matter because magnetars appear to be young by neutron star standards, and their strongest activity seems to fade over relatively short astronomical timescales. They are not common beacons that last unchanged for billions of years. They are more like compact remnants passing through a turbulent magnetic youth, bright in high-energy radiation for a while, then gradually quieting as the field decays and reorganizes. Their rarity among observed neutron stars may reflect this narrow window. Many old neutron stars may once have been more magnetically active than they are now, but only a limited number are caught in the stage when their magnetic fields are still powerful enough to announce themselves violently. The crust is where much of that announcement becomes visible. A neutron star crust is already an extreme solid-like layer, made from compressed nuclei and shaped by gravity. In a magnetar, magnetic stress can build within this crust and in the magnetosphere above it. The field may twist as internal motions shift. It may press sideways against rigid material that can resist for a time but not forever. When the stress exceeds the crust's capacity, the crust may crack or slip. The word quake is often used, though the resemblance to an earthquake is only partial. On Earth, Earthquakes come from moving tectonic plates and brittle rock. On a Magnetar, the motion comes from magnetic force acting on a dense nuclear crust. The scale of displacement may be small, but the energy involved can be enormous because the material is so dense and the magnetic field so strong. A tiny rearrangement of a magnetar's crust can release more high-energy radiation than the sun emits over a long span of ordinary shining. These events can produce bursts of X-rays and gamma rays. Some are brief flashes, lasting only moments. Others build into larger outbursts in which the star remains brighter for days, months, or years as the crust and magnetosphere relax. The most dramatic are giant flares, rare events in which a magnetar releases an immense pulse of energy. A flare can begin with a sharp spike of gamma radiation, followed by a fading tail modulated by the star's rotation. That modulation is a clue that the energy is tied to the rotating remnant itself. The flare does not come from a broad nebula or a normal stellar surface. It comes from a small compact object whose magnetic structure has suddenly rearranged. The pulse tail carries the turning of the neutron star through the afterglow, like a signature of the engine that produced it. The magnetosphere of a magnetar is not empty. It can hold charged particles, twisted field lines, and currents sustained by the enormous magnetic stress. When the crust shifts, the magnetosphere may respond, and when the magnetosphere untwists, it can heat the surface and alter the radiation pattern. The surface may show hot regions where particles return along magnetic field lines and deposit energy. Observed brightness can change not only because the star itself cools or warms, but because the magnetic field changes the route by which energy escapes. A magnetar is therefore a coupled system interior field: crustal strain, magnetospheric current, surface heating, and high energy emission. Each part influences the others. The object may look like a point of light to a telescope, but the point contains a layered struggle between rigidity and field, between stored energy and sudden release. Rotation plays a different role in magnetars than in ordinary rotation-powered pulsars. Many magnetars spin more slowly than young radio pulsars, often completing a turn in several seconds rather than fractions of a second. Their slow rotation might seem surprising until the magnetic field is remembered. A strong magnetic field can drain rotational energy efficiently, breaking the star over time. Yet the observed bursts and persistent high-energy glow are too powerful to be explained mainly by rotation alone. The magnetic field supplies the missing energy. This distinction helps separate magnetars from ordinary pulsars. A pulsar spends spin. A magnetar spends magnetic stress. Both are neutron stars. Both rotate. Both can emit beams or pulses, but their power sources are not identical. The same compact remnant category contains more than one kind of engine. Some magnetars blur those categories. A few have produced radio pulses after outbursts, behaving for a time in ways that resemble pulsars. Some pulsars have magnetic fields strong enough to approach magnetar territory, while some magnetars can become radio quiet and visible mainly through X-rays. These overlaps suggest that neutron stars do not fall into perfectly isolated boxes. Age, field strength, spin, environment, and internal history may place them along a wider continuum. A magnetar may be an especially magnetic phase of neutron star life rather than a wholly separate kind of object. The boundary is useful, but nature may cross it more freely than the labels imply. The decay of a magnetar's field also has long consequences. As magnetic energy dissipates, it can heat the crust and keep the star brighter in X-rays than an ordinary cooling neutron star of similar age. The field may rearrange gradually, producing smaller bursts and changing the pulse shape. Over thousands or tens of thousands of years, the strongest activity may fade. The star remains a neutron star. but the fierce magnetic youth gives way to a quieter remnant. Its crust may settle into fewer fractures. Its magnetosphere may carry weaker currents. Its signal may become harder to distinguish from the broader population of compact stellar remains. Magnetar power is therefore both extraordinary and temporary, at least in its most visible form. What makes magnetars especially revealing is the way they show that neutron stars are not only dense objects but stressed objects. Gravity compresses them, rotation shapes them, and magnetic fields can twist them from within. Their eruptions are not random fireworks. They are signs that a compact remnant contains stored energy in structures that can fail, slip, and reorganize. The field is invisible, but its consequences are not. It can heat a surface, reshape a pulse, fracture a crust, and send high-energy radiation across the galaxy. In a magnetar, the neutron star becomes a reminder that the most intense forces do not need a large stage. A city-sized remnant can hold a magnetic field powerful enough to make its own crust unstable. The next turn in the story brings that compact power into relationship with other stars, because a neutron star does not always age alone. In a binary system, gravity can feed it, spin it up, bury its field, wake its radiation, and make the remnant dangerous in a slower and more sustained way. Companions change the life of a neutron star because even a collapsed remnant is not finished if another star remains close enough to feed it. In isolation, the neutron star gradually spends its rotation, cools through radiation and neutrinos, and may fade from easy detection as its beam weakens or no longer crosses Earth. In a binary system, the story is less quiet. The companion becomes a source of matter, angular momentum, heat, and disturbance. Gravity reaches outward from the compact remnant and reshapes the outer layers of the neighbouring star, especially if the orbit is tight. Gas that once belonged to the companion can be pulled away and drawn toward the neutron star, not falling straight down at first, but curling into an accretion disk where friction, magnetic fields, and orbital motion turn the stolen material into a hot, luminous flow. The neutron star remains small, yet its influence can rearrange a system larger than the orbit of a planet. A companion turns the remnant from a cooling relic into an active engine again. Accretion begins when matter crosses the boundary where the companion can no longer hold it securely. In many close binaries, this happens through an inner gravitational gateway, where gas leaving the donor star flows toward the compact object. The gas carries angular momentum, so it cannot simply drop onto the surface. Instead, it spreads into a disk, circling faster as it moves inward. The inner disk becomes hot enough to shine strongly in X-rays, and the final fall onto the neutron star releases even more energy. Matter descending onto a normal star releases gravitational energy, but matter descending onto a neutron star falls into a much deeper well. By the time it reaches the surface or the magnetic boundary above it, a large fraction of its available energy has been converted into heat and radiation. A small amount of accreted material can therefore produce a bright signal. The system may look from far away like a point source, but within that point is a controlled transfer of matter from one star to the exposed surface of another star's dead core. The magnetic field decides how the final descent occurs. If the field is strong enough, it can truncate the inner accretion disk before the gas touches the surface. Charged particles then follow magnetic field lines toward the magnetic poles, striking limited regions rather than spreading evenly over the star. These hot impact zones rotate with the neutron star, creating pulses in X-ray brightness. The geometry can resemble a lighthouse, though the power source is different from that of an ordinary radio pulsar. Here the light is driven largely by accretion. Gravity supplies the energy, the disk supplies the matter, and the magnetic field supplies the path. If the neutron star spins rapidly, the rotating magnetic field may even fling some incoming matter away in a propeller state, preventing steady feeding until the balance changes. The system becomes a contest among inward gravity, rotating magnetism, and the angular momentum of the disk. Feeding also changes the star that feeds. A companion may lose its outer layers slowly, over millions or billions of years, becoming lighter and more altered as the neutron star strips it. Some donor stars are ordinary stars filling their gravitational boundary. Others are white dwarfs, already compact remnants themselves, transferring material through close orbital contact. The mass stream can heat the donor, change its structure, and expose deeper layers that would otherwise remain buried. In extreme cases, a companion may be reduced to a small remnant, perhaps only a faint object with much of its original mass removed. The neutron star is not merely receiving material. It is sculpting the future of the entire binary. For the neutron star, the most important gift from accretion may be spin. Gas in the disk carries angular momentum, and when it finally reaches the star or couples to its magnetic field, some of that angular momentum can be transferred. A neutron star that had slowed during isolation can be spun up again, gradually rotating faster and faster. Over long intervals, this process can create a millisecond pulsar, an old neutron star rotating hundreds of times each second. Such an object is often called recycled, not because the collapse has been undone, but because the binary has renewed the star's rotational life. The remnant is old in age, yet young in spin. Its surface may have been reheated, its magnetic field altered or partly buried, and its pulse made steady enough to act as one of the most precise natural clocks known. The companion has not restored the star to life in the ordinary stellar sense. It has restored its visibility, its timing power, and its place in observation. Accretion can also bury magnetic fields. As fresh matter settles onto the surface, it spreads under gravity and can push magnetic structures downward or rearrange the outer layers through which the field emerges. This may help explain why many millisecond pulsars have weaker magnetic fields than young pulsars. When accretion stops, the neutron star can reappear as a radio millisecond pulsar, now spinning rapidly with a more modest magnetic field. Some systems even move between states, showing accretion-powered X-ray behavior at one time and radio pulsar behavior at another. These transitional objects reveal that the boundary between feeding neutron star and recycled pulsar is not always fixed. A single remnant can pass back and forth depending on how much matter arrives and how the magnetosphere responds. On the surface, accreted material can ignite. Hydrogen and helium from the companion settle into layers, compressed by the neutron star's gravity until temperatures and pressures allow sudden thermonuclear burning. The result can be an X-ray burst, a rapid brightening caused by nuclear fuel igniting across part or all of the surface. These bursts are not supernovae, they do not destroy the star, they are surface flashes, driven by accumulated material burning under extreme gravity. Their rise and decay can reveal the size of the emitting region, the distance to the source, and the strength of the gravitational field. In some cases, repeated bursts show that the neutron star is gathering fuel in cycles, then burning it when conditions become unstable. The surface becomes a furnace again, but only in a thin accreted layer, and only because a companion continues to donate matter. The crust of an accreting neutron star is therefore not a frozen relic of birth. Fresh material is buried beneath new arrivals and pushed into higher pressure regions, where nuclei capture electrons, release neutrons, or fuse in unusual reactions. It is processed, heated, and rebuilt by the rain of matter from the companion. When accretion pauses, the crust can cool, and that cooling can be observed. Such observations help reveal how heat moves through the crust and how the interior absorbs or releases energy. The orbit itself evolves as matter moves. If mass transfer is stable, the system can persist for long spans, gradually widening or tightening depending on the masses and angular momentum losses. If it is unstable, the companion may be disrupted more violently, forming a dense disk or triggering a new phase of rapid accretion. Gravitational waves can also drain orbital energy from very compact binaries, bringing the stars closer together. A neutron star with a white dwarf companion may settle into a long-lived millisecond pulsar system after mass transfer ends. A neutron star with another neutron star follows a darker path, because orbital decay can eventually lead to merger. The companion determines whether the remnant is quietly recycled, repeatedly fed, or carried toward a final collision. In this way, binary life is not a side chapter. It is one of the main routes by which neutron stars change after birth. Companions make neutron stars more observable because they give them material to act upon. An isolated old remnant may be difficult to detect, but a feeding neutron star can shine brightly in X-rays, pulse from hot polar caps, burst from surface burning, and reveal its mass through the motion of its companion. Binary systems allow measurements that isolated stars often do not provide. The orbit can give mass, the burst can constrain radius, the accretion disk can trace gravity near the compact object. The cooling crust can speak for dense matter below. The companion is therefore not only a victim or supplier, it is also a measuring device, placed by nature in orbit around one of the densest visible objects in the universe. The strange power of a neutron star becomes clearer when another star comes near enough to feel it for a long time. It does not need to explode again to be dangerous or luminous. It can work patiently, drawing gas across an orbit, heating a disk, spinning itself faster, altering its magnetic field, igniting thin surface layers, and wearing down the body that feeds it. The remnant that began as the collapsed core of a supernova becomes part of a slower exchange, one where gravity is steady rather than sudden, and where transformation happens through orbit after orbit. In the next stage, that exchange grows more final. When the companion is another neutron star, feeding gives way to spiral, and two compact remnants can carry their dense matter toward collision, sending ripples through space-time and scattering heavy elements into the galaxy. When two neutron stars orbit one another closely enough, their future is written not in fire at first, but in loss. Each star moves through curved space-time, and because the pair accelerates around a common center, the system radiates gravitational waves. These waves carry energy away. The loss is tiny from one orbit to the next, yet over long ages it becomes decisive. The orbit shrinks, the stars move faster, the time between turns shortens. What began as a compact binary becomes an spiral, a slow tightening that can last for millions of years before ending in a final rush. Unlike a star feeding a neutron star through a disk, this system contains two objects that are both already collapsed. There is no broad atmosphere to peel away gently, no companion surface that can be heated and stripped over a calm sequence of orbits. There are two dense remnants, each with a crust, a core, a gravitational field, and a hidden interior near the limit of matter as they draw closer. Each star begins to deform the other. Tidal forces reach across the narrowing gap, raising distortions in objects that resist deformation with extraordinary strength. The degree of that distortion matters because it reveals how stiff neutron star matter is. A star with a larger, more easily deformed interior leaves a different gravitational wave pattern from one that remains compact and resistant. Long before the collision becomes visible in light, the motion of the orbit is already carrying information about the matter inside both stars. The final seconds are unlike the long waiting that came before them. The orbit tightens rapidly, the gravitational wave frequency rises, and the stars sweep around one another many times in a short interval. The signal grows into a chirp, not in sound travelling through space, but in the increasing frequency of space-time ripples detected far away. At the end, the surfaces meet, the crusts shear and tear. The dense cores collide in a region where gravity, nuclear pressure, heat, magnetic field, and rotation all act at once. The exact result depends on mass. If the combined remnant is too heavy, it may collapse almost immediately into a black hole. If it can resist for a time, it may form a massive, rapidly rotating neutron star, supported temporarily by heat and uneven rotation. If the support lasts longer, the remnant may shine as a powerful magnetized object before losing enough energy to collapse later, or it may survive if the total mass remains below the true maximum. The merger is therefore not a single fixed ending, it is a branching event, and the hidden equation of state helps decide which branch nature chooses. The collision throws matter outward. Some material is squeezed out by tidal forces before the final contact. Some is ejected in shock-heated plumes during the impact. Some forms a hot disk around the central remnant or a new black hole, while part of that disk may later escape in winds. This expelled matter is neutron-rich, meaning it contains many more neutrons than ordinary atomic material. When it expands into space, pressure falls, temperature changes, and atomic nuclei begin to assemble through rapid neutron capture. In this process, nuclei absorb neutrons faster than they can decay, building heavy elements that would be difficult to produce in ordinary stellar burning. Later radioactive decay reshapes those unstable nuclei into more lasting forms. Gold, platinum, and other heavy elements can emerge from such conditions, not as decorations added to the universe, but as products of violent dense matter returning to open space. The light from this radioactive debris is called a kilonova. It is dimmer than many supernovae but rich in meaning, because its colour and fading pattern reveal the presence of freshly made heavy elements. The debris can glow first in bluer light if some of it is less opaque, then shift toward redder infrared emission as heavier elements with complex atomic structures dominate the opacity. This glow is the visible afterword to a gravitational wave event. The waves announce the inspiral and collision. The kilonova shows that matter has escaped and begun making heavy nuclei. Together they provide a fuller story than either messenger alone. Gravitational waves carry the movement of mass. Light carries the chemistry of the aftermath. When both are detected from the same event, astronomy becomes multi-messenger astronomy, and the merger is no longer a distant inference based on one kind of signal. It becomes a linked chain of motion, impact, debris, radiation, and element formation. The first confirmed observation of a binary neutron star merger in gravitational waves, followed by light from the same region of sky, changed the way these objects were understood. It showed that neutron-star collisions were not only theoretical sources of ripples in space-time, they were also factories for heavy elements and likely engines for some short gamma-ray bursts. A short gamma-ray burst can occur when a compact remnant or newly formed black hole launches narrow jets of high-energy particles and radiation. If a jet is pointed near Earth, the burst appears bright and brief. If it is seen from the side, it may be fainter or delayed, with afterglow emission emerging as the jet interacts with surrounding material. The geometry is difficult, but the implication is clear enough. A merger can send signals through several channels at once: gravitational waves from the inspiral, gamma rays from relativistic outflows, optical and infrared light from the kilonova, and radio or X-ray afterglow from expanding material. One event can speak in many languages. The creation of heavy elements gives neutron star mergers a wider place in cosmic history. Ordinary stars make many elements through fusion, but fusion has limits. And the heavier stable elements require environments where nuclei can gather neutrons rapidly. Supernovae may contribute under some conditions, and the full accounting of element origins is still studied. But neutron star mergers are now known to provide a major pathway for rapid neutron capture material. This links the death of massive stars to the ingredients of planets and life in a delayed sequence. A massive star dies and leaves a neutron star. Another star in the system may also collapse, producing a second neutron star. The pair loses energy for ages through gravitational waves. Eventually they merge, ejecting neutron-rich matter. That matter becomes heavy elements, mixes into interstellar gas, and may later be incorporated into new stars, rocky planets, oceans, minerals, and living chemistry. The chain is long, indirect, and easily missed. Yet it means that some atoms in a planetary crust, a ring, a machine, or a living body may carry a history that passed through the collision of two collapsed stellar cores. The merger is also a test of the boundary between neutron stars and black holes. If the combined mass collapses, the final object may hide behind an event horizon, leaving the surrounding disk an ejector to radiate what remains outside. If a neutron star remnant survives temporarily, its rotation and magnetic field can inject additional energy into the debris, altering the light curve and perhaps producing stronger emissions. Observations of the fading light, the gravitational wave signal, and any high-energy counterpart can therefore hint at what the central remnant became. The answer matters because it constrains the maximum mass of neutron stars. A remnant that survives for even a short time suggests that dense matter can bear a certain amount of weight under particular rotational and thermal conditions. A prompt collapse suggests a lower limit on endurance. The universe uses mergers to press neutron star matter against its final boundary, and observers read the result from signals that travelled across cosmic distance. There is a quiet transformation in this. Earlier in their lives, neutron stars seem like endpoints, dead cores, collapsed remnants, final answers to massive stellar death. In mergers, they become beginnings again. They release material that had been locked under crushing pressure. They seed space with elements that can enter the next generation of stars. They turn gravitational collapse into chemical inheritance. The event is destructive beyond ordinary scale, but its consequence is not only erasure, it is redistribution. Matter that was once sealed inside the densest visible stars is scattered into a galaxy that can use it again. This is one of the reasons neutron stars feel so central to the larger story of matter. They are not just strange because of what they contain. They are strange because, under the right circumstances, they return part of that containment to the universe in a form that later worlds can inherit. The merger closes one life of compact objects while opening many quieter possibilities elsewhere. Yet even this powerful ending is not the only strange environment a neutron star can create. Some remnants hold planets in damaged or newly assembled systems. Some meet black holes, where their matter may be swallowed or torn apart at the last visible edge of gravity. The collision of two neutron stars reveals how destruction can become material. But the final limits of neutron star endurance appear most clearly when these dense remnants are placed beside objects even stronger than themselves. Planets around neutron stars seem, at first, like an error in the expected order of things. A planet is usually imagined as a companion to a living star, warmed by steady light and formed in a broad disk of gas and dust before the violence of stellar death arrives. A neutron star is what remains after that violence has already passed. Its parent star has collapsed, its outer layers have been driven outward, and the region nearby has been flooded with radiation, shock waves, and debris. Yet planets have been found around pulsars, and their existence shows that even a supernova does not always erase every possibility for orbital architecture. These planets are not gentle extensions of a normal solar system. They are survivors, captures, or second-generation worlds assembled from damaged material. They orbit a compact remnant whose light is not the warm continuous output of fusion, but the hard and intermittent radiation of a dead star's magnetosphere. Their presence does not make neutron stars hospitable. It makes them more complex because gravity can gather structure even after catastrophe. The first confirmed planets outside the solar system were found not around a sun-like star, but around a pulsar. Their discovery was unexpected because a pulsar seemed like one of the least likely places to preserve planets. The timing of the pulses revealed small regular variations, caused by the neutron star moving slightly around the shared centre of mass with its companions. In ordinary astronomy, a planet may be seen through dimming starlight or through the wobble of a star. Around a pulsar, the clock itself becomes the detector. A planet tugging on the neutron star changes the arrival times of pulses by tiny amounts, and because pulsar timing can be extraordinarily precise, even small companions can leave a clear signature. The result was a quiet reversal. The first worlds found beyond the Sun belonged to a system already marked by stellar death. Their existence suggested several possible histories, none of them simple. Some pulsar planets may be remnants of earlier planets that somehow endured the supernova, though survival through such an event is difficult and would require special circumstances. Others may form after the explosion from fallback debris, material that was thrown outward but did not escape completely, settling into a disk around the neutron star and gradually assembling into new bodies. Still others may be connected to binary evolution, where a companion star is stripped down until what remains resembles a planet more than a star. In that case, the planet is not a normal planet in origin, but the exposed core or reduced remains of a once larger object. Neutron stars can therefore host planets through pathways that are closer to salvage than calm formation. The bodies are shaped by loss before they are shaped by stability. Conditions on such worlds would be severe. A pulsar can bathe its surroundings in high-energy particles, X-rays, gamma rays, and strong winds from the magnetosphere. The habitable zone around an ordinary star is based on gentle thermal balance, where liquid water might persist on a surface under the right atmosphere. Around a neutron star, the problem is not only temperature, it is radiation, particle bombardment, atmospheric erosion, tidal effects, and the lack of steady sunlight. Some theoretical discussions have considered whether a very thick atmosphere or unusual shielding could protect a planet far enough from a pulsar, but such possibilities remain narrow and uncertain. The calmer conclusion is that pulsar planets are scientifically important, not because they are likely homes for life, but because they reveal how planet formation and survival can occur in damaged environments. They show that orbital systems can be rebuilt from debris, and that planets are not limited to the quiet youth of ordinary stars. A neutron star's reach becomes even more severe when the companion is not a planet, but a black hole. In such a pairing, the neutron star meets an object that has crossed the boundary it has not. The neutron star has a surface, a crust, dense matter, and signals that can escape. The black hole has an event horizon, beyond which outward communication ends. When the two orbit one another, gravitational waves carry energy away, and the orbit tightens. The final encounter depends strongly on the masses and spins involved. If the black hole is large enough, it may swallow the neutron star whole before tidal forces can tear it apart outside the horizon. From the outside, such an event may produce gravitational waves with little or no bright electromagnetic display, because most of the matter disappears before it can radiate freely. If the black hole is smaller, or spinning in a favourable way. The neutron star may be disrupted before crossing the horizon. Then its material can be stretched into streams, with some falling in, some forming a disk, and some perhaps escaping into space. This tidal disruption is one of the clearest demonstrations of neutron star fragility beside a stronger gravitational boundary. The star is among the densest visible objects in the universe, supported by nuclear pressure and quantum rules, yet near a black hole it can be unmade by curvature and tide. The crust that could support tiny mountains, the core that resisted collapse after a supernova, and the matter that survived as a compact surface can be pulled apart if the encounter happens outside the event horizon. The outcome is not only destruction. If enough neutron-rich material escapes, it may undergo rapid neutron capture and contribute heavy elements, much like debris from neutron star mergers, but the amount of ejected matter can vary widely. Some neutron star black hole mergers may be chemically rich and luminous. Others may be nearly dark except for the gravitational waves they send across space. The difference between these outcomes carries information about the black hole's mass and spin, and about the neutron star's radius and internal stiffness. A larger neutron star is easier to disrupt at a distance from the black hole. A more compact one may be swallowed more cleanly. Thus, even in defeat, the neutron star reveals its structure. The final moments of the merger become a test of how tightly matter was held before the black hole took it. These encounters point back to the central limit of neutron stars, the maximum mass they can support. A neutron star is not protected from collapse forever. If it gains too much mass through accretion, if it merges with another compact object, or if a temporary support such as rapid rotation fades, it may cross the threshold into black hole formation. The exact maximum remains uncertain because it depends on the equation of state of dense matter. Observed neutron stars with high masses prove that the material inside must be stiff enough to hold at least that much weight. At the same time, gravitational wave observations and radius measurements narrow the allowed range. The boundary is not just a number. It is the point where the resistance of a nuclear matter stops answering gravity. Below it, the object can have a surface. Above it, no known pressure can prevent further collapse. Rotation complicates the boundary because a rapidly spinning neutron star can support more mass than a non-rotating one. After a merger, a remnant may survive briefly because it is hot, differentially rotating, or magnetically supported. But heat escapes, rotation redistributes, magnetic fields evolve. If the remnant exceeds the stable limit once those temporary supports fade, collapse follows. The same object may pass through phases massive neutron star, unstable remnant, black hole. This makes the end of a neutron star life less like a single switch and more like a sequence of supports being removed. The object endures for as long as each layer of resistance can hold. When the last one fails, the surface is lost. The planets, black hole encounters, and mass limits all show neutron stars at the edge of categories. They can host worlds, but not in the ordinary warmth of a main sequence star. They can resist collapse, but not beyond a finite threshold. They can be more compact than almost anything visible, yet still be torn apart by a black hole. They can act as clocks, magnets, element factories, and gravitational probes, but every role depends on the fact that they remain just outside the horizon of disappearance. Their strange power is not only that they are extreme, it is that they are extreme while still available to observation. Light can leave them, pulses can mark them, matter can strike their surfaces, crusts can crack, companions can feed them, mergers can scatter their interiors. A neutron star is a remnant that has not withdrawn completely from the universe. It remains exposed enough to teach, dense enough to challenge, and unstable enough in the wrong circumstances to change again. the story closes, then, not with a simple final object, but with a boundary held for a time. A massive star collapses, but not always into darkness. Matter is crushed, but not always erased from view. A surface survives where gravity nearly wins, and across that surface the universe writes pulses, bursts, quakes, fields, collisions, and the slow cooling of a dead core. Neutron stars are not the largest things in the cosmos, nor the most hidden. Their power lies in the narrow place between those extremes, where a star has died and yet continues to make gravity, matter, light, and time behave in ways that remain almost beyond ordinary comparison. The strange power of neutron stars rests in the way they remain present after collapse. They are not living stars in the old sense, and they are not black holes hidden behind a horizon. They are the exposed remnants in between, small enough to make gravity severe, dense enough to remake matter, and visible enough for their signals to cross the galaxy. From a distance, they may appear only as pulses, bursts, faint X-rays, or subtle changes in the timing of another star. Yet each signal carries the memory of a massive star's ending, and the pressure of an object still resisting complete disappearance. Their surfaces cool, their crusts hold strain, their magnetic fields shift and decay, their rotations slow, or sometimes return to astonishing speed when a companion feeds them. In collisions, they give back some of their hidden matter to space, allowing heavy elements to drift into later clouds, later planets, and later chemistry. Nothing about them is gentle in structure, but their story can still settle into a quiet shape. A neutron star is a reminder that the universe often leaves its deepest questions in small places, where mass has been compressed, where light escapes with difficulty, and where matter exists close to the limits of its own identity. The mystery is not only what happens inside them, but how much can be learned from the few signs they allow to leave. A pulse, a cooling curve, a burst, a gravitational wave, a tiny shift in timing, each one is a narrow opening into a hidden interior. And beyond every measurement, the object remains there, turning slowly or rapidly in the dark, holding the remains of a star in a sphere no wider than a city, patient under gravity, still answering collapse with form,